Good afternoon, everybody. It's 4:30. It's just about time to get started. I'm just waiting a couple more minutes to see who shows up. Thanks. Okay, here we go. Good afternoon, everybody. Today, as you can see, we will be covering exponents. There have been, of course, uses of these already so far this course. We have been exposed to them, particularly in the geometry section, but here we're going to cover all of the rules of the exponents and how we use them. So, I'm going to deviate from the lecture notes just a little bit to start with. Just because I like to do this demonstration, it starts to make everything just a little bit more clear. Starting off with a very simple point, an exponent exists to show what happens when you're multiplying something by itself a certain number of times. So if I have this some number, we'll call it x, and it is multiplying by itself 3 times, we use the exponent 3. Multiplying 3 times, we have the exponent 3. Starting with that piece of notation and just holding on to that idea, I'm going to show you a demonstration of what happens moving through different levels of powers or exponents, and it will help make the exponent laws that I'm about to go through a little bit more clear. I need a little bit more space. So what I'm going to do here is I'm just going to draw out what we're going to do with these numbers. Oops, already have 3's. Okay, so 3 times 3 times 3 times 3. No problem. That's 3 to the 4th. That's what we're expecting it to be. As we move down here, 3 times 3 times 3, we're dropping one exponent. Oops, try that again. And what I would like you to take note of in terms of what's happening as we move down this little ladder is at each level, I'm dividing by 3. So if I have 4 3s, I divide by 3, then I'm down to 3 3s. And then I divide by 3 again, and I'm down to 2 3s. And then I divide by 3 again, and I'm down to 1 3. So that when we come down to ask ourselves now, what happens if I go down one more? Going from 3 to the power of 1 down to 3 to the power of 0, the exact same thing is still happening. We are dividing by 3. And it is worth noting that 3 divided by 3 is 1. And that's where we get the logic that anything raised to the power of 0 is going to be equal to 1. Following along this same logic, we can start to discover what happens when we go into negative exponents, right? So we're going down 1 every time here, go from 0 to negative 1. Well, I'm still dividing by 3, and in fact, we can show it directly. 1 divided by 3. Because once again, as we've gone down, we've simply divided by 3. And then that logic continues. If I wanted to find out what is 3 to the negative 2, well, again, we are dividing by 3. And our rules of fractions say when you divide by 3, you flip that second one and multiply. And so we end up with 1 over 3 squared, or 1 over 9. And it carries on all the way down. So that's sort of a quick demonstration of what's happening with our integer exponents going down, all of our whole numbers. We can see why we get to the 4 digits. We can see why we get to 0 because it's our base number divided by itself. We can see why we then get to negative numbers. It turns into a fraction because, again, we take our 1 divided by its base number, and all of a sudden our base is on the bottom of the fraction. So that's seeing it with real numbers. And now I'm going to flip back and start to follow exactly along the line with the lecture notes. And we'll go through these exponent laws, but this gives you something to hang those exponent laws on to start with. So in an exponential expression, like this one, A is called the base. So any number that's there at the bottom, that's called the base. And then this, of course, up here is called the exponent. Sometimes we also call it the power. And then we get into a bunch of laws that are based on this. So, as we just looked at, any number to the power of 0 is going to be 1, as long as your base itself is not actually 0. 0 to the power of 0 is not a defined number. You can't call it 1. So it's just worth noting that in all of these cases, we are not dealing with 0 as a number. The next law that we were looking at, what happens when we deal with negative numbers? Well, that tells us that we're dealing with this on the other side of the fraction line. Okay? You can put the 1 there as the exponent, but by convention, if it's to the power of 1, we don't write the exponent. It is worth noting here that no matter which side of the fraction line you're on, if your exponent is negative, you move to the other side of the fraction line. So if I had some number 1 over m to the power of negative 2, I could actually just rewrite that as m to the power of 2. The next part that I want to deal with in terms of negatives is taking note of where the negative falls in relation to your base. If you see something like this, you kind of want to break it out into all of its pieces. So the a squared part is the a times a, but that negative implies that we have a -1 out front of the whole thing, which is different than if I had some negative number in brackets, and then it would be all squared. So in that case, what I'd be getting is I'd be getting a -a times a -a, which actually would then come out to the positive version, because the negative times the negative is a positive. Moving along to interacting powers. If I have some number to the power of m, and I'm going to multiply that by some power of the same base, that's the important part, of the same base to the power of n, I can just end up adding these exponents. And I'll give you a demonstration of that. If I have 2 to the power of 4, and I'm multiplying that by 2 to the power of 3, that's the same as saying 2 times 2 times 2 times 2. There's my first 4, times 2 times 2 times 2. There's my next 3. If I count those up, that's a total of 7, which is the same as saying 4 plus 3. So for the most part, we can actually just jump from there to there. Another quick example, without the middle part, if I had 4 to the power of 7 times 4 to the power of 6, that would be 4 to the power of 7 plus 6, or simply 13. In the same way that when we are multiplying numbers of the same base, we add the exponents. If we are dividing numbers of the same base, we subtract the exponents. So my same a to the m and a to the n, if I have a to the m divided by a to the n, that is going to be a to the power of m minus n. Using the same quick examples, if I had 2 to the power of 4 divided by 2 to the power of 3, that would be the same as saying 2 times 2 times 2 times 2 over 2 times 2 times 2. And as we've seen in previous things, we can cancel these top and bottom, which just leaves me with 1, 2 in the end here, which is the same as saying, oops, wrong color. Same as saying 2 to the power of 4 minus 3, which just gives us 2. Moving along, if we have some number raised to a power and that whole thing is raised to a power, we multiply the powers. Why do we multiply the powers? Yes, we multiply the powers. So we do that because if I have 2 to the power of 4 raised to the third power, that's going to be the same as saying 2 to the power of 4 times 2 to the power of 4 times 2 to the power of 4, which as we just learned is the same as saying 4 plus 4 plus 4. And instead of adding, we could just go 3 times 4, in this case, 12. So instead of having to write out all of those steps, if I had 4 to the power of 6 raised to the 7th power, that's just the same as saying 6 times 7 in terms of the powers, and I get 4 to the 42. To answer the question that just popped up, Lauren, yes, you're absolutely right. That's what it equals. Last thing to note in terms of the power rules that we're pulling out, if you've got multiple numbers being raised to some power, it's the same as raising each of those numbers to that power. You can distribute the power. So this also follows when you're dealing with negative exponents. If I had a over b all raised to the power of -2, for example, the negative now applies to both of these things. So we're going to change sides of the fraction sign for both of them, and then I can apply the power to both of them. Okay, so I've tried to give examples of these things as we've gone along. There are a couple of other examples, really quick examples in the lecture notes. I'm not going to go through those. I'm going to jump straight to the first worked example. So we are being asked to simplify. Three to the power of -2 times 2 to the power of 3 plus 5 to the power of 0. That's a 0. There we go. Over 3 to the power of 3. Order of operations tells us the first thing that we do ahead of everything else is exponents. Where it goes brackets exponents. So we're going to do all the exponent work first. It's negative, so I know I'm going to be 1 over, and then 3 squared is 3 times 3, or simply 9. 2 to the power of 3 is 2 times 2 times 2, which is 8. 5 to the power of 0 is 1, and then 3 to the power of 3 is 27. From there, we can simply follow all of the things we're supposed to do. We need common denominators. That's what the fractions rules tell us. So 9 needs to match with 27. It's quite easy. We multiply it by 3. Whatever I do to the bottom, I must do to the top. And I end up with 3 over 27. 8 is not quite so easy. 8 does not deal with 27s nicely. So in the end, we have to multiply 8 times 27, top and bottom. And when we do that, we end up with, oh, sorry, I just realized I'm missing my own notation here. This is a multiplying. Sorry, before we do this, let me step back a moment. My apologies. This is still 1 over 9, but this is multiplying by 8 before we add. So I can multiply before we add 1/9 times 8, which is just 8 over 9. That'll make our job a little bit easier. We still have to multiply by 3, top and bottom, but now that takes our 8 into account, which makes our numbers much nicer. And we end up with 24 over 27 plus 1 over 27 for a final answer of 25 over 27. Okay, next worked example, unless there are other questions on that. Why not write 8 times 27 plus 1 times 9 over 1 times 27? I'm not sure I understand. Let me just write out what I think you're asking here, Lauren. So you're talking about... Oh, you were talking about up here? Oh, at this stage here. I don't know that it necessarily would be easier. I think you get to the same place. If that makes more sense in your head, I would follow that.
Yeah.
Okay, I'm going to come back to that. I want to think about what you're asking there, and we'll come back around to that. Okay. Next question we're asked to simplify is negative 2 to the power of 4 plus the whole of negative 2 to the power of 4. I wanted to do this example really quickly just to reinforce the difference between these two things, something in brackets being raised to the power, something outside of brackets being raised to the power. 2 to the power of 4 is 16, so this first one becomes negative 16. Negative 2 to the power of 4 is also going to be 16, and because I have an even number of powers, my negatives are going to disappear. Those of you who are not quite seeing why my negative disappears there, I'm just going to do this over here. This becomes negative 2 times negative 2 times negative 2 times negative 2. With each pair, negative times a negative becomes a positive, so that becomes a positive 4. And the same thing happens here, a positive 4. And then my positive 4s multiply together, and I end up with my positive 16. So, having done that, negative 16 plus 16, and we end up with 0. Okay, simplifying expressions with exponent terms. Simplifying an expression containing exponential parts, we need to have as few exponential terms as possible. Usually this involves carrying out the operations that are in the expression. So we're trying to simplify it down as much as we can, and we want to have no terms with negative exponents. The reason why we want to have no terms with negative exponents has never been well explained to me. It largely has to do with convention over time. Just one of those things that people expect is that you're going to get rid of all of the negative exponents. So that's what we do when we simplify an expression. Again, we're being asked to simplify. And let's take 3 squared times a to the power of 3 times b squared, all to the power of 3. And this gets multiplied by 4 to the negative 3, a to the 3, b to the negative 8. And we get to assume that a and b are non-zero. So the first thing we want to do is we want to deal with our numbers. We want to turn those into whole numbers without exponents because it's the easiest thing to do with both of them. 3 squared is 9. And I'm going to carry that a to the 3, b to the 2 with me for a second, and we're going to keep that cubed. 4 to the power of negative 3 4 to the power of 3 is going to be 64, and it's a negative exponent, so I end up with 1 over 64. A to the 3, and B has a negative exponent on it too, so I end up with 1 over B to the 8th. Next thing I'm going to do is I'm going to apply this exponent outside the bracket. It has to share by each thing inside the brackets. So I end up with 9 cubed, A to the power of 3 times 3, which is 9. I'm going to do that a little bigger so it's a little easier to read. 9 cubed, A to the power of 9, B to the 3 times 2, which is B to the power of 6. And then nothing has changed here. I'm just going to clean it up a little bit. I'll get A cubed on top. I will have 64 and B to the 8th on the bottom. Now I can multiply these two sides together. While I do that, I'm going to take my 9 and I'm going to raise it to the 3rd power. And I end up with 729, A to the 9th, B to the 6th, times A cubed, and then on the bottom I still have my 64 B to the 8. The only reason I've done this is so that you can see that I'm going to take my A's of they're the same base, so I can put those together and I end up with 729 A to the 12th, B to the 6th, over 64 B to the 8th. Now I can have my B's interact. This is going to be a subtraction, so 6 minus 8, which gets me to -2. We don't want negative exponents, so I'm going to leave it on the bottom. 729 A to the 12th over 64 B to the 2. Okay. Everyone's still with me? Okay, so just about half are in that stage of a little lost, but keep going, I'll catch up. So I'm just going to stop and clarify a couple of things on this question then to make life a little bit, hopefully a little bit easier. At this stage, I should point out that that goes with that, and they add. That's how we get the 12 there. Here, those subtract. And because it's a negative, we want it on the bottom of the fraction, so we put it there. Those are the two pieces I skipped over a little bit quickly, so hopefully that'll help clarify some things for some people. The 729 came from the 9 cubed, 9 times 9 times 9. Okay. Let's go on to another worked example. So again, we're going to simplify, and I have x to the power of -3 plus y to the power of -1 over x squared. So the very first thing we want to do is get rid of all of those negative exponents. So we're going to get everything on the right side of the fraction lines. First one becomes 1 over x cubed. The y wants to come to the other side of the fraction line, so we leave a 1 up top, and we end up with x squared y. Now we just have a pair of fraction questions we have to deal with. I need to get this side up to an x cubed, and I need to put a y on this side in order to make these balance. So what that's going to look like is this is going to multiply by x over x, and this side is going to multiply by y over y. And we end up with y over x cubed y plus x over x cubed y, which we can simply leave as y plus x over x cubed y. Why wouldn't it be x squared divided by y? Because there is no negative on this exponent. Because there's no negative on this exponent, it doesn't change where it is in the fraction line. Only the y has the negative, so it's the only part that moves. Does that make sense? Great. Any other immediate questions on this before I move on to fractional exponents? Excellent. Okay. Fractional exponents. I had it on my little pre-class picture, but I'll show it again. So if you have, well, we'll start with the notes. An exponent in the form of a fraction, like 1 over n, represents what we call the nth root of a number or of a base. The root is that number which, when raised to the nth power, gets you your original number back. That's a really fancy way of saying if I have 1 over n and I multiplied it by n, I'd end up with a power of 1. Okay, so if I had some number, I'll do it the other way too. If I had some number x raised to the power of 1 over n, and I multiply and I raise that, to the power of n, ultimately I'd just end up with x. These would cancel each other out. Now, because we're dealing with the nth root of things, what we're ultimately dealing with are radicals. That's what that sign is. That is called a radical sign. And the reason it is called a radical sign is because of the word, what the word radical originally meant, which was to go back to the roots. So ultimately, we are again getting back to the root of something by using the radical. While I'm sitting here doing this and showing little things, when we have something like this, I have x to the power of 1 over n. I'm looking for the nth root of x. When I move that, I can throw that into a radical. Whatever that number on the bottom is goes in that little check mark part to show us which root we're dealing with. And the x goes there, and then whatever number is on the top part of the fraction remains the power on the base. Then we go through a bunch of examples with this stuff in sort of a whole bunch of different forms, and then I'll show you what we can do in terms of working problems with it. So we start off with a fairly straightforward example. If I have 49 to the power of 1/2, it's the same as saying I would like the square root of 49. It's worth noting you don't often see the 2 that goes on in here. It's implied. If you don't see it, you assume that there is a 2 there. That's what we mean by the square root. And that gets us to 7. And the reason for that, of course, is because 7 squared gets us back to 49. So you can see that 2 1/2 relationship. If I had 8 to the 1/3, this would say that I'm looking for the cubed root of 8, which is 2. And that is true, I know, because 2 to the power of 3 gets me 8 back. So when we're dealing with fractional exponents with 2 numbers larger than 1 on top and bottom, an exponent like m over n can be thought of as taking the nth root to the mth power. And you could also go the other ways around. You could take the mth power first and then take the nth root. You end up with the same result either way. I'll show you. I'm going to do it both ways so you can see it. So let's say we have 4 to the power of 3 over 2. What this is essentially saying in one form is that I want the square root of 4 raised to the 3rd power. So I'll do this part inside brackets first. The square root of 4 is 2. And then that gets raised to the 3rd power. And as we saw earlier, 2 to the 3rd power is 8. I can do the exact same question, but this way I can do it. I want to take the square root of 4 to the 3rd power. 4 to the 3rd power is 64, and the square root of 64 is 8. So you can see it really doesn't matter which way you go with it. It works out the exact same way both times. Now, it is worth noting that when we're dealing with fractional exponents, those exponents that are fractions are still fractions, and they behave like fractions. That should be 3 over 2. Three on top, 2 on the bottom. When we're dealing with fractional exponents, the fractions in the exponents are still fractions. So if I have 4 to the power of 3 over 6, well, 3 over 6 reduces. So I can go ahead and just reduce that fraction down to 1/2. Which, as we learned just now, is the same as asking for the square root. So we just take it, and we're good. Okay, a worked example. Nine to the power of negative 1/2 plus 2 to the power of 4 over 2 minus 3 to the power of negative 2. Nine to the power of negative 1/2. There's a couple of things happening in there at the same time. We have the negative, which is telling us to put it on the other side of the fraction, and then we have the 1/2, which is asking us for the square root. So Because of the negative, the first thing I'm going to do is 1 over, and then I will take the square root of 9. And there's my 3. The next thing we want to do is we come over here. We have 2 to the power of 4 over 2. Well, 2 goes into 4 nicely, so this can actually just reduce down to 2. So 2 squared is 4. And then again, we have this negative part that we want to deal with. This tells us we're going to put it on the other side of the fraction, and then we're going to square it. So I end up with 1 over 9. And now I want everything with the same denominator. The lowest common denominator for all of these is going to be 9. So this will multiply by 3. We'll treat that as over 1, and it will multiply by 9. When we do that, I end up with 3 over 9 plus 36 over 9 minus 1 over 9. The bottom stays the same because we're adding and subtracting. 3 plus 36 gets us 39, minus 1 gets us down to 38. So far, so good, fairly simple and straightforward. However, when we get into some of the more complicated things, like I'm about to throw up right now, we want to make sure that we're keeping track of all of our pieces. So I'm going to try and take as much room for this as possible. And when you guys are doing your work, I suggest you also take as much room as possible. Most mistakes happen just because we're trying to rush through the steps. So we are being given, all in brackets, 27, a to the power of 6, b to the power of negative 7, c squared, all over 3, a to the power of negative 2, the letter b, and then c to the power of 4, and the whole thing is being raised to the power of 1/2. For myself, I find it easiest to do everything inside the brackets before trying to apply that external exponent. So what's going to happen is I'm going to work on the inside, and this 1/2 is just going to carry down until we're ready to use it. So what can I do to make my life easy to begin with? I'm going to simplify top and bottom. 3 goes into 27 9 times. A to the 6th over a to the negative 2, that becomes a subtraction question. I'm going to write it out really explicitly just so that we can keep track of everything. So this becomes 6 minus negative 2. I know it's a weird way to write out the powers, but I want you to see what's happening clearly here. I'm getting a to the power of 6 minus the negative 2 from the other a. So a to the power of 6 minus negative 2. I'm going to do the same thing with my b's. I'm going to keep it all up. Oh, that's a bit tall. All up top for the time being. I'm going to get b to the negative 7 minus 1. Just to be clear, that 1 comes from the implied exponent on the b. And then finally, I'm going to take c to the power of 2 minus 4. And now I have nothing left on the bottoms. We're fine, and that 1/2 comes for the ride. Now we can simplify everything inside here. The 9 stays as it is. 6 minus negative 2 is the same as saying 6 plus 2, so we end up with a to the power of 8. Negative 7 minus 1 becomes b to the negative 8. 2 minus 4 gets us negative 2. This is all still in brackets and all still raised to the power of 1/2. Now I'm going to apply this exponent. Remember, it shares with each thing in here. So we have to use that 1/2 4 times in this case. When we do that, I end up with 9 to the power of 1/2. I end up with a to the power of negative 8 over 2. I end up with b to the power of, a is a positive 8 over 2. B is a negative 8 over 2. And then c is simply negative 2 over 2. Nine to the 1/2 is the same as asking for the square root of 9, so it becomes 3. A to the power of 8 over 2, 2 goes into 8 4 times, so we have a to the power of 4. The negative tells us we want it on the other side of the fraction line, so the b is going to come down, and again 2 goes into 8 4 times, so I have b to the power of 4. C is negative, so it too comes to the bottom of the fraction, and 2 over 2 is to the power of 1, so we don't need to write anything, and we can finish off there. Any questions on how we got to the finish of that question? Excellent. Okay, so now that we've been introduced to fractional exponents, and we can now move on to start dealing with radicals and radical expressions. I know you've been waiting your whole lives for this moment. It's just too exciting. So, now we're into radicals. Radical expression is simply one that's involving the root sign or the radical sign. So basically, the same rules of exponents still apply. I'm going to do out a couple of these rules just so that things are nice and clear, and we'll then use those going forward to figure out a couple of problems. If I have some number a times b under the radical sign, that's the same as saying taking the square root of the a times the square root of b. No problem. Same thing works with the division. If I have the square root of a over b, that's the same as taking the square root of a on its own and dividing it by the square root of b on its own. No problem. There are a few rules when we're simplifying these things that I've made note of in the lecture notes. For radical expressions to be in simplified form, we need for an nth root, there must be no nth powers as a factor inside the root. What do I mean by that? So, in essence, what that means is if you put it back into a fraction, could you simplify it? If I had some number x to the power of 3, and I was inside something to the 6th power, that would be the same as saying x to the power of 3 over 6, which simplifies down to 1/2. So in fact, to be simplified under the radical, we should have no powers inside. So when it says for an nth root, there must be no nth powers as a factor inside the root, that's what we mean. If you could turn it into a fraction and simplify it, you must do so. There are no fractions under the radical sign, which ultimately means that what it's looking for is this form, not that form. And if the expression is a fraction, there are no radicals in the denominator. So in the end, it doesn't even want that square root of b. And I'm going to show you how to deal with square roots or radical signs in the denominator through some examples, and you can see how to get rid of them. Okay. Let's go through a couple of examples. So on that first thing, for an nth root, there should be no nth powers as a factor inside the root. So if we have something that's asking us to simplify the square root of 40, because of that implied 2 that goes in that check mark right in there, we're looking for anything where we can take out powers of 2. When we do that, or in order to do that, there's a couple of ways we can do this. I'm going to show you a quick way if you know how your times tables work. And if you're not as comfortable with your times tables, I'll show you a longer but guaranteed way at the same time. So 40 we can simply recognize as being 4 times 10. And the reason, I mean, there's a number of ways you can get to 40, but I choose that way because I know that 4 is a square, which is to say I can take the square root of it. Which means I'm getting the square root of 4 times the square root of 10. I take that square root of 4 and it's just 2. So I end up with 2 root 10. The other way I could do this, if I'm not quite as comfortable with all of that, is I can do what's called a factor tree. I'm going to do this in a different color just so that it's clear that it's a different process. And with a factor tree, you're just trying to break things down to all of its smallest basic factors. So 40, it's an even number, so I'll divide it by 2, which will leave me with 20. 20 also divides by 2, which leaves you with 10. 10 divides by 2, and that leaves me with 5. Ultimately, these are the numbers that I'm interested in, the ones at the end of the branches, and I'm looking for pairs of numbers. Okay? Because of the implied 2 there, I am looking for pairs of numbers. Do this in black. There's a pair of numbers. Okay, there's a pair of 2s, so I can bring those out and just call those one of the 2s. I have no other pairs, so these numbers stay inside my radical. Okay, so I end up with 2 to the power of 2 times, and then radical 2 times 5. I can put my 2 times 5 together, and again I end up with 2 radical 10. So your pairs, one can come outside. Anything that isn't a pair stays on the inside. I'm going to do that one more time, this time with a cube root, so you can see what happens if it's not just pairs. So this time I'm going to ask for the cube root of 24. So now instead of looking for pairs, I'm looking for groupings of 3. If you can figure these things out in your head fairly quickly, it's fine. So we're going to take the square root of 24, and we will recognize that that can be broken down to 3 times 8. Square root of 3, or sorry, cube root. This is cube roots everywhere. Cube root of 3 times the cube root of 8. The cube root of 8 is 2 times 2 times 2, so just 2. And then we leave the cube root of 3 there. If that's not as obvious to you, again, we can break it down as a factor tree. 24 divides by 2, and it leaves me with 12. 12 divides by 2, leaves me with 6. 6 divides by 2, and it leaves me with 3. When I look at it, there's a grouping of 3, so I can bring one of those outside, and then that 3 stays inside. So I end up with 2 cube root 3. Sorry, I'm being told the camera's a little out of focus. Let me see what I can do here. That's worse. Too far. Is that better? If I made things worse? Sort of the same. Let's see what I can do here. And yes, I will try and write things bigger so that my exponent 2s and exponent 3s are just a little bit more clear. I'll try and do it bigger. Let me rewrite this bigger, and you'll tell me. Tell me if that works. So let's go with cube root 24. So cube root 24 becomes cube root 3 times cube root 8, which just becomes 2 cube root 3. Is that better? Okay. Okay, so now let's move on and take a look at what happens when we have radicals in our denominator. Sorry, why does it become a 2? It becomes a 2 because 8 is 2 times 2 times 2. So we have groups of 3, okay? So that 8 could become 2 times 2 times 2. Because it's groups of 3, we can bring it outside. We can take its cube root. Is that clear? Okay. What happens if we're given something like the square root of 5 over 2? Well, as we were looking at earlier, that's the same as saying the square root of 5 over square root of 2. However, we're not allowed to have radicals in the bottom of our fractions. So I'm going to get rid of it. How do I get rid of it? I'm going to multiply it by itself, top and bottom. Because when I do that, square root of 2 times the square root of 2, I'm just left with 2. Those square roots cancel each other out. And then on top, well, 5 times 2 is 10. So now I've gotten rid of that radical on the bottom. It's not always that easy, but we're going to start with it that easy and go from there. The other thing that we want to start to notice about radicals is that they function a lot like questions where you're asked to gather like terms. Okay, so anything that's got the same radical on it can be collected. What do I mean by all that? So let's say we have square root 75, square root 20, plus the square root of 12, plus the square root of 45. First thing I'm going to do is I'm going to simplify all of these. I'm going to do it the fast way. If you have questions about where something came from, do ask me and I will try to clarify it. So 75 is the same as saying 3 times 25. 25 is a perfect square, so it can come down to 5 square root 3. Square root of 20 is the same as saying the square root of 4 times 5. I can take the square root of 4, and it's a 2. Square root of 12 is the same as square root of 4 times 3. Again, I can take that square root of 4, and it leaves the 3 behind. And then the square root of 45 is 9 times 5. I can take the square root of 9, and the 5 comes along. So just to be clear, square root of 25 becomes 5. Square root of 4 becomes 2. Square root of 4 becomes 2. And the square root of 9 becomes 3. Now that I've done that, I look for things where I can put stuff together. So in this case, my 3's, I got two things where the square root of 3, so I can put the 5 and the 2 together. And I end up with 7 root 3. Same thing happens with my square root 5's. I can put, those are the same, so I can put these together. And I end up with 5 square root 5. And then there's nothing else that simplifies, so we're done. One more worked example, combining the two ideas. How do we rationalize the denominator, which is to say, how do we get rid of the radical on the denominator while still simplifying all of our radicals? And in this case, our question is going to read square root of 6 plus the square root of 7 all over square root of 8. First thing I can do is I can simplify that one. That's as simple as it gets. There are no squares hidden in 6. There are no squares hidden in 7. But there is a square hidden in 8. It's 4. So this becomes square root of 6 plus the square root of 7 all over 2 root 2. Those of you who are wondering what happened there, this became square root of 2 times 4, and then the 4 was a square, so it came out over there. So now I can take my root 6 plus root 7 over 2 square root 2, and I go, oh, I have a radical on the denominator. I'm not allowed to do that. So this is going to multiply by square root of 2, top and bottom. And when we do that, I end up with square root of 6 times the square root of 2 plus the square root of 7 times the square root of 2 all over 2 square root 2 times the square root of 2. But we can simplify all of this now, and I end up with square root of 12 plus the square root of 14 all over 2 times 2. We're not quite done. We need to clean this up a little bit. I'm going to bring it back up to the top just because I've run out of room. So I'm here. I've got square root of 12 plus the square root of 14 over 2 times 2. Well, there's a square hidden in 12. It's 4 times 3. There is no roots hidden in 14, however, so it stays on its own, and 2 times 2 becomes 4 on the bottom. I can take the square root of 4, so it becomes 2 root 3. Square root of 14 is as simple as it can get, so we leave it alone, and then 4 stays on the bottom. Now, for those of you who are probably wondering, why am I not simplifying the 2 here? The reason I cannot simplify this 2 with this 4 is because I don't have anything corresponding on the other radical. The number in front of this here is a 1, so it doesn't divide by 2 nicely. Because I can't divide everything by 2, I divide nothing by 2. Okay. Unless there are any more questions on that, I'm going to keep moving. I want to get to a point where I can give you guys a chance to stretch and have a break, and then we'll do some questions. All of the previous requirements for exponential expressions to be simplified still apply as we move forward, and this is now the default rule. As we move forward on these tests, you'll be expected to be able to simplify radicals and to rationalize the denominator, which is to say, get rid of the radicals on the denominator. And no negative exponents. So, we will do one more quick example just so that you can see how something must end up. And then I want to go back to trigonometry just for a quick question so you can see how our use of radicals helps our trigonometry. Then we'll take a brief break. So, let's pretend we've just done a fairly long, involved problem. We've simplified everything down, and we get to this point, we go, oh, okay, we're done. And the answer is no, we are not done. We have bunches of problems. We have a huge radical over an entire fraction. We're not allowed to have that. We have negatives in our question. We're not allowed to have that. And at the end, we want to make sure we have no radicals in our denominator. So, whole bunches of pieces of work to be done. First thing we're going to do is we're going to get rid of that negative exponent. That negative exponent says it wants to go to the other side of the fraction line. So I'm going to take my 27, I'm going to leave it on top, and I'm going to end up with y x to the 5th on the bottom. Next thing I'm going to do is I'm going to break out my radicals. So I end up with square root of 27 on top, and I end up with the square root of y x to the 5th on the bottom. Now this x to the 5th has a couple of squares in it that I can pull out. Just do a quick sidebar here. X to the 5th is the same as saying x to the 4th times x. And if I have this under a radical sign, I can then take the square root of x to the 4th, and the square root of x to the 4th is x squared. So I end up with an x squared times x. That's how that comes about. So on the bottom here, I end up with x squared on the outside, and then x and y on the inside. At the same time, I can take a look at 27, and I'll do the same sort of sidebar. And 27 is the same as saying 3 times 9. I can take the square root of 9, and I end up with 3 root 3. So that's what I get here. Now we're very close to being done. But again, we have this radical on the bottom here. We don't want that radical on the bottom. So I'm going to multiply by x square root of xy, top and bottom. And when I do that, on the top, I end up with 3. Everything under the radical multiplies together, so I end up with 3xy. It's getting a little squished, sorry. And then on the bottom, the radical is what cancels out, so I end up with x squared times xy, which is to say x cubed times y. Okay. Any questions on that? Sorry. So what happens here? I'm actually gonna erase the upper stuff, and I'm gonna spread this out and explain it out in a little bit more detail, just so that people can see it. So I'm here, I'm at 3 square root 3 over x squared root xy. And this is being multiplied by xy over, or root xy over root xy. When we do this, we're of course multiplying straight across. So the 3 just comes along for the ride. That's no big deal. Root 3 times root xy all comes together, and I end up with 3xy. That's no problem. On the denominator, what we end up with, and if I do this out in excruciating detail, we're going to go with the x squared comes for the ride. Square root xy times square root xy ends up being square root x squared y squared. The top is just going to continue to come for the ride for a little while, so that's 3xy. The x squared comes along. I can take the square root of x squared, it's x. I can take the square root of y squared, it's y. Again, the numerator, the top comes for the ride, 3xy. X squared times x gets me my x cubed, and then the y comes along. Does that clarify for everybody? Why is the x squared equals, okay, so square root of x squared, the way one wants to think of this, I think I'm looking at the right one. If I have an x squared under the radical sign, the squared and the radical cancel each other out. Yes. Cool. Okay, one more quick example. I figured there's got to be a bunch of people who are ready to stand up and stretch for a minute. So let me go through the last little thing that I just wanted to explain. When I was talking about trigonometry last, one of the things that I mentioned was with our special triangles, we can't just write things the way they come up. So a quick recall on our special triangle. if I have, oh, let's do this bigger so it's clearer here. If I have 30 degrees there, 60 degrees there, and a right angle there, I should have 1 root 3 and 2. Yes. Okay, so that's our special triangle. We end up with this root 3. So if you're dealing with, let's say, just for a quick example, cosine of 30 degrees. Remembering our SOHCAHTOA, this, by the way, is a good habit. Whenever you're dealing with a trigonometry question, you're not quite sure where you're going. First thing you should really do, write down your SOHCAHTOA so that you can remember what all of your relationships are. Okay, so I've just written down cosine so I can remind myself, oh right, cosine is adjacent over hypotenuse. So there's my adjacent, and there's my hypotenuse. This becomes nice and easy. I end up with root 3 over 2. No problem. My radical's on top, not an issue. But let's say I'm dealing with the tangent of 30. Tangent is opposite over adjacent. So now, that's my opposite, that's my adjacent. So I end up with 1 over square root of 3. And that's what we're not allowed to have, is that square root of 3 on the bottom. So it is sort of taken as given, because that's the way it reads when you just put it out, that what you are going to do is you're going to rationalize that denominator automatically in your head, so that the answer we actually come out with should be root 3 over 3. So if somebody's asking for the tan of 30, you're looking at your special triangles, you want to automatically convert it to that form. Okay, and the same thing holds with your other special triangle, your 45-45 triangle, where that's 1, and that's the square root of 2. That's your hypotenuse, which means that for the sine of 45 and for the cosine of 45, you would end up with your radical on the bottom. Like that, and that's not how we want it. In the end, how we want it should be root 2 over 2. Okay. Last thing to show you on all of this goes with the Pythagorean theorem. I'll do a quick example. We can now continuously have exact answers when we're doing something like this. So we're given a triangle, 3, 15, some unknown. Our Pythagorean theorem, of course, a squared plus b squared is equal to c squared. So I will take it as a, b, c. 3 squared plus x squared equals 15 squared, so 9 plus x squared is equal to 225. X squared, sorry, we'll just do this really quickly, minus 9 is equal to 216. Now we can actually take care of this properly. So now I'm going to take the square root of my x squared. and that's going to be take that away, and I then need the square root of 216. Without going through the full factor tree on this, this is the same as saying 6 times 36. I can take the square root of 36, and I end up with 6 root 6. So that's the exact answer. Okay, it is 10 to 6. We have half an hour left. I've had some requests to do take a look at a couple of questions from the homework for trigonometry, so I'm prepared to go ahead and do that. If anybody else has questions in the trigonometry they would like me to go over, feel free to get those prepared. And in the meantime, I'll let everybody take a 5-minute break. So I will start up again at 5:55. Okay, I have had a number of requests. I think I have them all. Multiple requests to go over question 5 from the trigonometry homework. I'll start off with that one, no problem. We'll also be taking a look at questions 11 and 16. I've had multiple requests for 16. And asked to be looking at special triangles. Well, fortunately, question 16 will help us look at special triangles, so we'll be able to do that. I've heard a request to simplify rules, and I've had a request to look at question 4F, and a question 10 if we have time at the end. So, seeing as how nobody said anything about the exponents homework, I'm assuming this is all from the trig homework. Oh, which reminds me of something I meant to lead with off the top. My apologies to all of you who submitted your exponents pretest and then had nothing happen with it. A great number of you got them in. I discovered late today, about 10 minutes before class, that my notifications had been turned off. So thank you to the student who brought that to my attention. I've turned the notifications back on, and hopefully all of you who have submitted your exponents pretest now have access to the homework. Okay. Let's start by just refreshing ourselves on the trig homework. So we're going to start by looking at question number 5, which says determine the quadrant and the reference angle for the following. And I'm just going to make note of these really quickly. 415 degrees. 11 pi over 30, 330 degrees, 4 pi over 3, 115 degrees, and 9 pi for 10. Okay, I've just scribbled those down. I know they're a little blurry for you guys, but they're mostly there for my reference. I'm going to make it all a little bit more clear over here. When you're being asked to find the quadrant for something, sorry, I just realized I should have the quadrant and then the reference angle. We'll start off with the quadrant stuff because it's just a little bit easier to visualize, and once you've figured out your quadrant, then it's much easier then to figure out your reference angle. So in order to figure out your quadrant, you want to draw yourself a reference circle of some sort, a unit circle. Okay, so this is your unit circle. That's your 0 point, or if you've gone all the way around the circle, it's also the point where you're at 2 pi. Okay? If you've only gone halfway around your circle, then you've only gone around by pi. Okay? And then doing it again, we're going to cut your pi and your 2 pi, or your 0 to pi in half. So literally we're at pi over 2 as we're halfway through. We can do the same thing going the other way. At the bottom, again, we're halfway between pi and 2 pi, which really means we're at 3 pi over 2. So far, so good. When we do something like that, now you've got an idea of where everything stands. The other thing you might want to do, again, because we're going to be dealing with radicals and degrees all at the same time, just remind yourself what this means in degrees. This is 0 over 360 degrees. This is 90 degrees. This one is 180 degrees. And this one is 270 degrees. So I'll start with question A, looking for 415. Well, 415 is larger than 360, so let's get rid of a 360 to start with. And when we do that, we end up with 55. 55 is between 0 and 90, which means it's in this quadrant. That's our closest x-axis, so we can actually just take it as red, okay? 415, our reference angle, is going to be 55 degrees, and we're in quadrant 1. Okay, dealing with radicals. There was the question, should you turn these into degrees first? You certainly can. There's nothing wrong with taking all of your radicals and turning them into degrees and then going through this same process. But if you can also work with it in radicals, down the line as you continue your mathematical education, it just becomes a little bit easier. If you're not feeling comfortable with it right now and you're just like, I just need to get this under my belt to start with, go ahead and turn them into degrees first. But what I'm going to show you is that you can identify your quadrant actually a lot faster just from the fraction part when you're in radicals. So let me start with that. Taking a look at 11 pi over 30. 11 pi over 30, ignoring the pi part just for a second, 11 over 30 is pretty close to 1/3, right? It's one way to think of it. Okay, so we could say that's approximately pi over 3. And all you really need to know about that is that that puts it between 0 and pi over 2. Immediately, this tells you that we're in the first quadrant. Okay. And that means that your reference angle is going to be exactly where it falls. I'm trying to get this about right. It's actually not too different from our 55 degrees in this case. And then you can go through the process. Sorry, let me finish off that thought. Because we're in the first quadrant, whatever the angle is the reference angle, because we're immediately making our angle with this first x-axis. So we'll go ahead and we'll turn this into degrees. We've been through this process before. We know that 180 degrees matches with pi. We've done that there. And this then has to match with the degrees that we're trying to find, and 11 pi over 30. I know that's a little bit tiny. I'll make this larger as I come through here. So then what we're looking for are fractions on this. I'm going to put it in the easy form. I'm going to put x on top, 180 on the bottom. Will be equal to 11 pi over 30 over pi. The pi's are going to cancel. I end up with 11 over 30 multiplied by 180. Where did that come from? I'm jumping really quickly here. 180 multiplies on both sides so that it cancels on this side. The other thing we can cancel, 30 goes into 180 really nicely. It goes in 6 times. So we just end up with 11 times 6, or 66 degrees. Which is why I was trying to draw it pretty close to our 55 degrees here. Oh, you can't see that bottom part. There we go. We do the same thing going through all of this. I'm going to clean out some of this extra writing. Basically, your process the whole way through. 330, we come all the way around. We are there-ish. Our reference angle has to go with this. Okay, so we're looking to come back up to the 8 here, which means we're ultimately looking for that. How do we find that? 360 minus 330 is 30, so our reference angle is 30. And we're in the 4th quadrant. Okay, with this next one, you can't always do this, but I want to try and show you a fairly quick and easy way to switch between your radians and your degrees, certainly for all of your big easy numbers. So 4 pi over 3. If I had 3 pi over 3, I would just have a single pi. So 4 pi over 3 is just a little bit bigger than that, and that brings us into this quadrant over here. And so we're looking for this as our reference angle. So we have to just figure out, well, how much farther have we gone from pi to 4 pi over 3? I'm going to take some time, and I'm going to try and explain this in a long way, but the whole idea behind what I'm explaining is to make a shorter mental path between your radians and your degrees. So if this seems confusing, please ask me questions, because I want you to see this. Remember, our ultimate goal is to figure out what is this thing here? What is that angle going on there? At 4 pi over 3, let's give myself a little more space than that. We are some distance from our 180 line or our pi line. We want to know how far. Well, pi could also be written as 3 pi over 3 because anything over itself is just equal to 1. So when I take a look at this, I'm going to go 4 pi over 3 minus 3 pi over 3. That should just leave me with 1/3. Sorry, and that should be 1 pi over 3. The pi's don't cancel. I have 1 pi over 3. Which is also to say just simply pi over 3. Pi over 3, looking at this really, really quickly, if I take pi and I divide it by 3, I could also make that the same as saying if I have 180 degrees divided by 3. Okay? Remembering that our ratio that was set up earlier when we convert between radians and degrees is 180 matches with pi. So I can replace that pi with 180 right away. And it just tells me that I'm immediately jumping down to 60 degrees. For those of you who can't quite see that. So if 180 matches with my pi, which means that I could say that this is 180 divided by 3. 3 goes into 180 60 times. So my reference angle becomes 60. And then because this is my 60 degrees here, I have to also remember that I'm going to be in quadrant 3. I've got the question, is it only quadrant 1 where the reference angle is the same as the start angle? And the answer is yes, it is only in quadrant 1 where your reference angle. So only those angles between 0 and 90. Okay, So I'm going to do one more. I'm just going to do the 115 degrees just so that you can see quadrant 2 for a second, and then I'm leaving 9 pi over 10 for all of you to practice on your own without having been given the answers. There's still questions about it on Thursday. I'll go over that one again. So here we are at 115 degrees. 115 degrees is bigger than 90 but less than 180, so it's somewhere in here. Our closest x-axis is in here, so we actually want that part. So I'm going to take 180 degrees. I'm going to subtract my 115 degrees. And I end up with 65 degrees. So that becomes my reference angle, and I'm in quadrant 2. Any other questions on that before I move on? Okay, good. So next, we've had, in order of the questions that I have as they are listed, we're going to move on to question 11. This is largely a calculator question. So, using a calculator, find the approximate value of each of the following rounded to 2 decimal places. Again, a couple of ways you can do this. The first one is fairly straightforward. Whenever you're dealing with it in degrees, just go ahead and do it in degrees on your calculator. So if I have the sine of 28 degrees, now it depends on the calculator that you have. You're either going to push the sine button and then punch in 28 and hit equals, or you have to punch in 28 first and then press your sine button and then press equals. And it all depends on the calculator that you've got. However, if you've done it right to 2 decimal places, you should have, well, it's going to come out looking like this to start with, and it goes on and on and on and on. We only want it to 2 decimal places, though. The 9 tells us we go up, so we're at 0.31. The next question is asking for the tan of pi over 10. We can still do this with a calculator. And as I say, there are 2 ways you can do this. You can start by converting this to degrees first, okay? And I'm going to do it the fast way again. So remembering that pi can be translated into 180, we could say that pi over 10 is the same as saying 180 over 10, or simply 18 degrees. Okay. Then you can put that in here. Into your calculator, sorry, and you should end up with 0.3249 on and on, which for our purposes means 0.32. I'm being told my calculator did the wrong thing. Hold on a second. Let me just double check it. Sine of 28. Sorry, what did I write down? Oh my. You're absolutely right, folks. I'm not quite sure what I punched in. 0.46947, etc., which should be 0.47. My apologies, my calculator, or I punched something funny into my calculator. I lost the 0 because in my head I was jumping to the answer too quickly. Thank you for pointing that out. Good. This is the easiest method for doing this. There is a way where you can go ahead and you can do this with radians directly, but it involves making sure that your calculator is in radians. And sometimes, depending on the calculator, that doesn't always come out with consistent answers, I've found. So for the most part, this is the easiest way to do it. Take your radians, convert it to degrees, and plunk it back in. For the record, though, if you are comfortable using radians on your calculator, also make sure that you're using your brackets correctly. So in this case, if you're going to do this, if you put your calculator into radians mode, you want to make sure that when you're doing this, you're doing in brackets the tan of pi divided by 10. Just to be clear, up here, your calculator should be in degrees mode. And you'll still end up getting the exact same answer. Any other questions on that? If we're all good with that, I want to move on to question 16. So, coming down to look at question 16, find the exact value, if it is defined, for each of the following. Sine of 270 degrees. We want the tan of pi over 2. We want to look at the cosine of 0. And then we want to look at the cosine of 3 pi over 2. Okay. There's a bunch of interesting manual ways that you can go about doing this, but here's one of the things. If you find yourself being asked for the exact value of something, this generally means that you are referring to your special triangles. In this case, and I'm just suddenly remembering what I've done with all of these questions here. In this case, though, we're looking at some very, very specific things. So I want you to see where this falls on your unit circle first, all of these things where they fall on your unit circles, so that the answers make just a little bit more sense to us. Let me flip back to my camera. There's our unit circle. 0 or 2 pi. There's pi. Pi over 2. And 3 pi over 2. And then, of course, in degrees, so we're also dealing with degrees. We're dealing with 0 or 360. 90, 180, and 270. Okay, so when it's asking for the sine of 270, that means that what we're looking at is right there, the angle that's formed when it's doing that. Sorry, that's not coming out very clearly. Let me see if I can make that a little more clear. When our angle is right there, okay? In order to work with special triangles, we're always working in reference angles, okay? Special triangles means reference angles. Reference angles are always between 0 and 90. So if I'm here at 270, that immediately means that my reference angle must be 90. Okay? So 270 degrees as a reference angle. Well, let's see if I can put some space there. Reference angle of 90 degrees. And funny things happen at 90 degrees because it's not really a triangle at that point. We don't generally take the angles of 90 degrees because when we're doing that, it means that our hypotenuse and our opposite are the exact same side. So we can't really do it. So I'm going to refer you back, excuse me, I just need to switch screens. I'm going to refer you back to that supplementary sheet that I was sharing with you guys when we were doing trigonometry. And we have special things that happen here at 90 degrees. So you can see for the sine of 90 degrees, it's going to be 1. When we get to 270 degrees, it's -1. And I'll explain that one in just a second. But it's worth noting that at 90 degrees and at 180 degrees and at 270 degrees, 360 degrees or 0, you always get some funny things happening. You can see we're only at 1 or 0 where things disappear. This handout is available on the website. It's trig, I think I called it trig table brackets supplementary. Okay, so this table is actually going to give us the exact answers for all of the questions that we're looking at, but I just want to explain where the positives and the negatives come from. So remembering that things came out when I was talking about this, oops, you guys can't see what I'm doing. Let's try that again. This quadrant is positive, positive. This quadrant is negative, positive. This quadrant is negative, negative. And this quadrant is positive, negative. Somebody clever figured out what that means in terms of all of our trig values. Oops, wrong. Starting in the bottom right-hand corner, you can write the word cast. Okay? And what this means is, in this quadrant, everything's positive. A stands for all. In quadrant 2, it means that sine is positive, which means that when you're dealing with your reference angles and you have something fall into this quadrant, unless you're dealing with the sine of that angle, it's going to be negative. But if you are dealing with the sine of that angle, it will be positive. Moving into the third quadrant, tangent is the only thing that's positive. Everything else is negative. And then into the fourth quadrant, cosine is positive and everything else is negative. So 270 degrees tells us, well, it's right on the border, but either way, it's either in the third or the fourth quadrant, which means that sine is negative. Okay? Because our sine is negative, our answer ends up being negative 1. Same thing ends up happening with each of these. With cosine of 0, we're going to end up at 1. And it's going to be positive because we're either in the first or fourth quadrant, and cosine is always positive there. Tangent of pi over 2 is undefined, or as I like to say, no. The reason for that is you end up dividing by 0. You're simply not allowed to divide by 0. Cosine 3 pi over 2. So again, we're going to be down here. I'm trying to remember if that one's a 1 or a 0. These things tend to slip my mind. Cosine 3 pi over 2 is 0. So for future reference, you can come back to this circle and you can work all of these things out the way that I was just showing you. Or, because somebody's already taken the time to do all of that work, make sure that you have available, particularly when you're in the test, that sheet. It'll help you with your major conversions between radians and degrees. Okay? And it shows you the exact values. Okay, question 4 was the next one that somebody was asking me for. So coming back up, find the smallest positive coterminal angle for each of the following. And we were specifically asked about this, so we're going to take a look at that. Smallest angle coterminal to 13 pi over 10. So given 13 pi over 10, our easiest course of action is first and foremost to convert this into degrees. I know immediately, because I'm 13 pi over 10, which is to say I'm a little bit bigger than 1, but I'm not as big as 1.5. I'm going to be somewhere in quadrant 3 here. Where exactly, I'm not sure yet. But we do a quick conversion and we'll find out. So this becomes 13 over 10 is equal to x over 180. We'll multiply by 180 on both sides. And that will come down to 18. 18 times 13 on your calculator comes out to 234. So 234 is somewhere in here. Let's say 234. And that is going to be your smallest, sorry, that was habit. I always, as soon as I'm doing something, I'm looking for the reference angle. Because I'm at less than 360, 234 is the angle that is coterminal. Oops, page. Okay, any further questions on coterminals? Or does that work for everybody? Okay, the next thing I have on my list is that I was asked to simplify the rules that I'd gone over in terms of the stuff that we had today with radicals. So I'm just going to make this really, really simple. Always simplify. One, simplify radicals, which is to say, if you've got root 20, that should actually read as 2 root 5. If you can make it simpler, make it simpler. No negative exponents. So if you have 1 over x to the negative 2, make it x to the 2. If you have y to the negative 5, you should make that 1 over y to the 5. And finally, no radicals in the denominator. So 1 over root 3 should be written as root 3 over 3. Okay. Next, I was asked to do question 10, and which should also cover off special triangles. So question 10, just to remind everybody, actually says, using special triangles, find the exact value of each of the following. So we're going to look for the sine of 30 degrees. We're going to look for tan of pi over 6. We're going to look for the cosine of 45 degrees. We'll look for the cosine of pi over 4. And we'll look for tangent 60 and sine pi over 3. I'm going to, what's going on here? So, I'm sharing the wrong thing here. Come on, computer. Really quickly, let's go back and look at those special triangles. Oops. Where'd they go? There they go. Okay. I'm trying to make these bigger and it's not being cooperative. There we go. Oh, the resolution on that is poor. I will redraw them. Okay, let's get out of there. Okay, so really quickly, I just sketched those out so we'd have them here to refer to. This is your 45-45 triangle with 1, 1, and root 2 as your sides. This is your 30-60-90 triangle with 1, root 3, and 2 as your sides. So let's start at the top. It asks for the sine of 30. Let me just get our SOHCAHTOA down here. Sine of 30, so it wants opposite over hypotenuse. There's my 30 degrees. My opposite is 1, and my hypotenuse is 2. So the sine of 30 degrees is 1 over 2. This is asking now for the tan of pi over 6. Pi over 6, really quickly, it's like saying 180 over 6, which is just 30. So we want the tangent of 30 degrees. Tangent is opposite over adjacent. So for my 30-degree angle, my opposite is 1. My adjacent is 3. So this becomes 1 over root 3. And as we just learned, we're not allowed to do that. So it becomes root 3 over 3. Last one, I've just been made aware of the time. I've gone over time, so this is the last one I'm going to have time to do right now. Cosine of 45 degrees. Cosine is adjacent over hypotenuse. Here's 45 degrees. My adjacent is 1. My hypotenuse is 2, so that says 1 over root 2, which, as we just learned, is root 2 over 2 when we simplify it. Why? What did the answers in the homework say? Oh dear. Let me take a peek. Yes, because I see. No, it's not that the answers are wrong. It's just that for the time that we had put together the answer key, I hadn't established the rule with you guys yet that we were trying to simplify the denominator or rationalize that denominator. Now that we know that that's what we're supposed to do, those answers start to look wrong, but they are the equivalent of what we're doing, which is why I had the 1 over root 3 here, because that's what you're going to see in the answer key. I like that better. For the trig test, I'm okay with this, but after the trig test, we are looking for it like that. Does that make sense? Was that clear? Okay. Okay. That's everything that we have time for today. Oh, there's my camera. There we go. If there are other questions that you'd like me to go over, we still have Thursday, and I will be prepared to answer questions on Thursday. If you have to take off, go ahead and take off. If you have specific questions you'd like me to go over before you try and take the test on Thursday, let me know in advance so I have those ready to go right at the beginning. Otherwise, I'm going to assume that people will be coming in. Some people will want to do the fractions and geometry tests. If you're planning on writing that, please do let me know in advance if you can. Otherwise, I'll take your name at the beginning of class. And the trigonometry exponent test will also be available on Thursday for those who feel they are ready to take it. And for everybody who's not ready to take any sort of test at all, I will be here answering questions. Okay, that's everything for this week, or for today, folks. I'll see you everybody on Thursday. Thank you, Jenna. Lauren, I will try and send you an email on those. So make a note right now. Okay, I've got those noted. Thank you, Lauren. I can definitely send you emails on those. Okay.